Hello, everybody. This is Dr. Ekstrom, and this is the first of a series of 7 short video lectures describing the science content for our second workshop on creating content-based digital games on the structure and energy of matter. So this time the workshop on November 1 is going to be in Holdridge. We're looking forward to working with you there. In these video lectures, I'm going to pretty much just run straight through the content, and then at the workshop itself, I'll be incorporating some simulations and activities, maybe some exercises, and possibly reorder things a little bit there. And so basically, just want this to be a content resource for you. And in the second workshop, we're really going to be focusing more, we're going to move from the atomic scale to the molecular and the compound scale and talk about mixtures and pure substances and phase behavior, solid, liquid, gas, and what happens in terms of energy content when we see these changes. The last video in this series is about some unusual phase behavior that I hope you and your students will find interesting, but we'll go ahead and go on. So where we left off with properties of atoms and atomic structure, we talked about John Dalton's atomic theory and how it was revolutionary compared to how many scientists were thinking at the time, and it was really essential to help help with the transition in terms of the development of chemistry from alchemy to something more toward our modern view of how compounds or substances are formed and how they react with one another. And there were a couple of postulates in Dalton's theory that were particularly revolutionary. First is that atoms of different elements may combine with each other in a fixed, simple whole number ratios to form compound atoms. And this whole idea is very different that most scientists and alchemists at the time really thought that different substances were entirely different at the atomic or molecular level than any sources that they came from. And so the idea that you could have recombinations of atoms create totally different substances is really something very new. And then as fifth postulate, atoms of the same element can combine in more than one ratio to form 2 or more compounds. It was also completely new. However, Dalton did not just simply pull these out of thin air. There were some experiments that were going on at the time that led Dalton to generate these ideas. The first was the law of conservation of matter. And Antoine Lavoisier, who I think we talked about a little bit in the first workshop, really led the way in terms of experimental evidence for this. I'm sure you all know when you teach your students that the law of conservation of matter is neither gained nor lost during a chemical reaction. And so we said in the first workshop, it's really only nuclear processes that can result in changes in mass for an entire system. Well, Lavoisier, you may recall, studied mercury, and heating mercury in an air environment created a compound that we know as mercury oxide. And what he would do with this mercury oxide was decompose it. And in this decomposition, he isolated all of the oxygen that was removed from the sample and measured the mass of that and the leftover mercury, and was able to show that that mass equaled the original mass of the mercury oxide to begin with. The other great discovery that started Dalton thinking along the lines of our modern atomic theory is Joseph Proust's experiment that is called the law of constant proportions or law of definite proportions. And this states that in a compound, the constituent elements are always present in a definite proportion by weight. And this is one of those principles that probably seems obvious on the surface to us, but back in the 18th century, it was really very important to establish that substances were A particular substance had a specific fundamental composition, and this kind of went against some of the principles of alchemy. And this principle really started to separate modern chemistry from alchemy principles. And so what he would do is he analyzed several sources of what turned out to be the same compound, and found through decomposition experiments that they each had the same atomic weight ratio. So an example picture at the right is calcium carbonate, that whether that source comes from an agate geode, or a patina on a roof, or simply in powdered form, all three sources had the same atomic ratio. And so in addition to that's copper carbonate shown on the right. He worked, in addition with copper carbonate, he worked with sodium chloride, water, calcium carbonate, and cinnabar, which is the mineral form of mercury sulfide. So Dalton then added to these experiments, and he actually worked on producing compounds that he found were made of the same elements but had different weight ratios. For instance, he would combine carbon and oxygen, heat these together, and found that he could make two different compounds. And in weighing them, he found that compound 1 had a 3 to 4 weight ratio between carbon and oxygen, whereas a second compound had a 3 to 8 ratio. So uh, after observing this, he thought, well, what could these compounds be? And one thing I find interesting is that Dalton started with an assumption. And the assumption was that the lowest ratio must come from a compound where one carbon atom combined with one oxygen atom. Personally, I think this is a little bit of a risky assumption. It turned out to work well with the carbon-oxygen case. Compound 1 is carbon monoxide, so one atom of carbon, one atom of oxygen. The 3 to 4 weight ratio comes from the fact that the oxygen atom is a little more massive than the carbon atom. Oxygen has more protons and neutrons than the carbon atom does, and so that leads to that weight ratio. And compound 2 then had to have twice as much oxygen. And so if the first compound has a formula of CO, the second compound must have a formula of CO2. So that compound 2 is known as carbon dioxide. Now, when we talk about substances that contain more than one element, we need to have some terminology straight. A molecule is a fundamental particle consisting of at least two atoms bonded together. And so some of these are very simple, like water and carbon dioxide. Water molecule has two hydrogen atoms and one oxygen atom, whereas a carbon dioxide molecule has one carbon atom and two oxygen atoms. So other molecules are much larger and more complex, such as sucrose, which is a form of sugar. It has a total of 45 atoms, 12 carbon, 22 hydrogen, and 11 oxygen. Now, we have other compounds, however, that don't necessarily break down into molecules. And for example, table salt, sodium chloride, that's considered a compound. A compound being a substance that forms from two or more elements that are chemically bonded together. However, we don't think of sodium chloride as breaking down into molecules, and that's because of the nature of the bonding. In molecules, there's a different type of bonding, we call it covalent bonding, than what we have in compounds like table salt. There, we're looking at ions that are attracted together, and we're going to talk in more detail about these forms of bonding here later on. Sometimes we find that there are some elements that actually break down into molecules instead of individual atoms. If you look across the periodic table, actually most elements can break down into individual atoms, but there are a few exceptions, and they all happen to be nonmetals. And so it might be interesting, if you weren't aware of this, might be interesting for your students to know. We have a series of diatomic molecules, meaning we have two atoms bonded together. And a lot of these your students are probably familiar with: hydrogen, nitrogen, oxygen. are all very common, and they exist as molecules. And also the halogen elements, fluorine, chlorine, bromine, and iodine. They all break down into molecules with two atoms bonded together. The interesting thing about the halogens, fluorine and chlorine are gases. However, bromine is a liquid and iodine is a solid, and yet they all break down to these analogous molecular forms. And so there's actually good reason for that too. And we're going to talk about intermolecular forces that actually lead to this kind of behavior. Two very interesting cases where elements break down into more complex molecules are phosphorus and sulfur. Phosphorus breaks down into P4 molecules when it is in the white phosphorus form. White phosphorus is an extremely flammable compound. Well, I should say substance. It's an element, but it breaks down into molecules with 4 phosphorus atoms that are arranged in a tetrahedron. And this is shown in the bottom center here of the slide. This bonding structure has a lot of strain. It's very difficult to hold these atoms together in this geometry. And so as a result, white phosphorus is very flammable, very explosive, and in fact has to be stored submerged in water so that air cannot get in contact with it. And then lastly, sulfur. Sulfur breaks down. Sulfur is a very, it's a yellow powder. Its molecular structure, you can have crystals of sulfur, but those very easily break down into more amorphous textures. And that's largely a result of the fact that the 8-membered rings that form. So sulfur breaks down into molecules with the formula S8. These are very floppy and lead to sulfur having a very often very amorphous type properties. So that's it for now, and so we'll continue our discussion in the second video.